So in this video, what we are doing is just a whole bunch of sample problems to practice all of our skills with equilibrium before we move on to the next section, which is on equilibrium and solubility. So this is a LeChat's principle problem. As with all of these review problems, you can give them a try on your own and then go through the video and see how you did, or you can just follow along. So this question gives us an equilibrium. A couple things that I noticed first is that this delta H is positive, which means the reaction is endothermic, and we can consider heat to be one of the reactants. That may become important a little bit later on. So the first question says, in which direction will the equilibrium shift when N2O4 is added? So remember, when we add, we shift to the opposite side. N2O4 is on the reactant side, so it's going to shift to the right. It's going to make more products. What if NO2 is removed? Well, if I remove something, it's going to shift to the same side. NO2 is on the right-hand side of the reaction, so again, this reaction will shift to the right, to the product side. What if the pressure is increased with the addition of N2? So N2 is not in the equilibrium. So what that means is that although it may increase the total pressure of the system, the partial pressure of the gases is not going to change. I mean, of the N2O4 and the NO2. So if you think of what K would be for this, right? Would the concentrations of any of those actually change? Well, no, the pressure of those wouldn't change. So K would stay the same. So this would have no effect. Now, what if I change the pressure by what D is going on in D? The volume is increased. If I increase the volume, yes, the partial pressures of each of those compounds is going to change. When the volume is increased, pressure is decreased. So pressure and volume are always inversely proportional. As one goes up, the other goes down. And if the pressure is decreased, then the opposite of that would be increasing the pressure. And increasing the pressure would be to shift to the side with more moles of gas, which again is the right-hand side. The side, if I think of this side, has 2 moles of gas and the other side only has 1 mole of gas. And the temperature is decreased. Remember, just think of heat or temperature as one and the same. So if the temperature is decreased, it's like removing one of the reactants. So remember, when I remove, it shifts to the same side. So the reaction is going to shift left, which would mean the concentration of the N2O4 would go up and the concentration of the NO2 would go down. So this question is another question about LeChat's principle, but it's looking at the numerical value of K in response to temperature. So he says, using the standard enthalpy of formation from Appendix C, determine the standard enthalpy change for the reaction. So that would be something that we did last chapter. Sometimes I don't teach this in between. I don't teach this before we do thermo, so I just did A for us. So that's what products minus reactants would give us for that. And then B says, how would the equilibrium constant for this reaction change with temperature? So if delta H is negative, that tells us that this reaction is exothermic. And because this reaction is exothermic, heat can be thought of as a product. So when I increase the temperature, the reaction will shift backwards to the left, which would mean more reactants would be made. If you think of the general equilibrium constant as being products over reactants, if the denominator becomes a larger number, then the value of the equilibrium constant gets smaller. So K would decrease as temperature increases. Remember, what changes what changes the equilibrium constant is just temperature. So the next practice question that we have is an integrated exercise that's going to have a whole bunch of the concepts that are in this chapter in it. So it gives us an example of a reaction that happens at 800 degrees Celsius. That's important for making a fuel called water gas. And we can see carbon solid with water at obviously really high temperatures makes carbon monoxide and hydrogen gas. And it gives us the equilibrium constant in Kp, so pressure. And it wants to know what's the equilibrium partial pressure of the other gases. And it gives us saying that we're starting with solid carbon, it's not going to be involved in the equilibrium because it is a solid, and 0.1 moles of water in a 1 liter vessel. So because this problem gives us Kp, and I'm eventually going to need to put in some X's into an ice chart and solve a quadratic in order to get those values, I can't just put in 0.1 over 1 liter. I can't put in the molarity in the ice chart. I actually need to calculate the pressure of the water to put that in the ice chart. So I did that ahead of time, right? PV equals nRT, divide both sides by V. So it's nRT over V. And when I plug all those numbers in, I get 8.81 ATM, which means that, my solid carbon, I'm not going to worry about. My H2O is going to be that 8.81 ATM, and I start out with 0 of those. And of course, this will go down by some value X, and these will go up by X, all the same X's because they all have the same coefficient. So 8.81 ATM minus X, and then X, and then X. So now this is when I use my equilibrium constant expression, right? That 14.1, that's the Kp. And that will be the pressure of the carbon monoxide times the pressure of the hydrogen gas over the pressure of the water. And plug those in for X. So 14.1 equals X squared over 8.81 minus X. And now I just need to solve this equation, right? Multiply or cross multiply, however you want to think about it. X squared is equal to 14.1 times 8.81 minus X. What do we get now? Let's see. X squared equals, I'll multiply these two together and to bring it over at the same time. So I multiply 14.1 times negative X, and then I bring it over to the left-hand side. So it's going to be positive 14.1X. And then I'm going to multiply 14.1 times 8.81, and then bring that over to the opposite side, minus 124.22. And so that will be equal to 0. So this is the format that I need to put it in order to get it into the quadratic equation. And remember, you can do this on a computer or your calculator, or just use the quadratic formula. And you're going to get two numbers for X, and one of them will make no sense. So the two numbers that you get for X are 6.14 and negative 20.238. And it's that negative number that doesn't make any sense, right? How can you have 0 carbon monoxide pressure and then have less than 0? That doesn't make any sense. So this guy we can rule out, which means that X is 6.14. So now I can come back over here and just actually plug in, 6.14, 6.14, 6.14 to make the equilibrium partial pressure of the water at 2.67 ATM, 6.14 ATM for the carbon monoxide, and 6.14 ATM for the hydrogen gas. Okay, so that's the first question there. Oh, I smushed it really small. The next question, so did we answer the question, equilibrium partial pressures of those two? Yes, we did. The next one says, what is the minimum amount of carbon required to achieve equilibrium under these conditions? Well, if I think about, where does this carbon come from? The only place that this carbon comes from is that solid carbon. So if I could figure out how many moles of carbon monoxide are made, that's how many moles of carbon I must have needed to start with, because they have a 1-to-1 mole ratio. So really what I'm going to try and figure out is the moles of carbon monoxide. I have the pressure of the carbon monoxide, so it's just working backwards from there, right? PV equals nRT, or N equals PV over RT, right? The pressure is that 6.41 ATM that we found in the last problem. This is 1.00. R is 0.0821 liters times ATM over moles times Kelvin. And that temperature is at 1073 Kelvin. When I plug all those guys in, I get 0.0697. And that is the moles of CO created. So that must mean that that is equal to the moles of carbon needed to start. Okay. What's the total pressure in this vessel? Well, this is Dalton's law of partial pressures. The total pressure will be the pressure of the water plus the pressure of the carbon monoxide plus the pressure of the hydrogen gas. Remember, the Carbon is a solid, so that will not contribute. All we need to do here is add them up. So that's going to be 2.67 ATM plus 6.14 ATM plus 6.14 ATM, or 14.95 ATM. D says at 25 degrees Celsius, so that's much lower temperature than the 800 degrees Celsius, Kp for this reaction is 1.17. Is this reaction endothermic or exothermic? So you have to sort of think about, okay, reactants make products, and at high temperatures, there's a, what was our equilibrium constant there? 14.1. And at low temperatures, our equilibrium constant is 1.7 times 10 to the negative 21. So remember that an equilibrium constant is the ratio of products over reactants. So at high temperatures, there's a lot more products. So what that means is that the reaction is going to be endothermic. Because when I add heat, right, the reaction will shift to the right. It will make more products. That will give it a larger equilibrium constant. And that's what we see in the numbers. And then E says, to produce the maximum amount of carbon monoxide and hydrogen at equilibrium, should the pressure of the system be increased or decreased? Well, in general, this reaction is 1 mole of gas converting to 2 moles of gas. I'm just looking at the coefficients for the species in the reaction that are gases. And if I want to maximize the amount of these, I want to shift the equilibrium to the right. We know that, so I want to shift to the side with more moles of gas. And that happens when I decrease the pressure, because the system will want to increase the pressure, and so therefore it will shift to the side with the more moles of gas. So if I want to maximize the amount of carbon monoxide and hydrogen, I would want to decrease the pressure. And this is just an overall practice-free response question. So it says, consider the reaction below that is allowed to reach equilibrium at certain temperature. And I see that it's endothermic. Write the Kp for this reaction. What this question is testing you is, number one, do you know the difference between a Kc and a Kp? And do you realize that this is an heterogeneous equilibrium, and we're not going to have to put the solids in there? So just the pressure of the CO2. That's all Kp is. B says, what are the optimum conditions of temperature and pressure that would lead to a large percent of CO2 in the gaseous mixture? So I want to make sure that I am forcing the reaction to the right-hand side, to the product side. I know that it's endothermic because this is positive. So I can put heat over here. So I know that if I want to push it to the right-hand side, I want to increase the temperature. So I would say a very high temperature would push the equilibrium to the right. And then pressure, if I increase the pressure, the system will try and decrease the pressure, so it will shift to the side with less moles of gas. So I don't want to increase the pressure, I want to do the opposite. I want to have this at low pressure. Therefore, the system tries to do the opposite, increase the pressure, which would be shifting to the side with the more moles of gas, and that's the side with the carbon dioxide on it. So high temperature and low pressure would be what I wanted to go for there. And then this is the same one, and it basically, you check one of these boxes and then give an explanation in terms of Q and K, or just give an explanation of it. So the first one is CO2 is added to the system, right? Remember, when we add, we shift to the opposite side. So if you add CO2, it's going to shift to the left. So we're going to check that box. Right? And if you think of why is it that, what will happen in terms of Q versus K, remember that Q is the products over reactants. If CO2 is added to the system, then the products will get larger. So therefore, the reaction will shift to the opposite side in order for the Q to come down to where K is. So this would be a case where Q is greater than K. And when Q is greater than K, we know it shifts to the left-hand side. The volume of the container is decreased. That's really another way of saying you're increasing the pressure. When you increase the pressure, it shifts to the side with less moles of gas, which is again the left-hand side. We're not working with Q and K here. Calcium oxide is removed from the system. Well, this is a solid, so removing the solid should not have any change in the equilibrium. Think of how Q would change. Q would not change, right? So if Q doesn't change, K doesn't respond to a change in Q.